These examples go with Lesson 10.1, Testing the Goodness of Fit. Example 1. Find the alpha equals 0.05 critical value for the chi-square distribution with 18 degrees of freedom. So what they're asking us to do is to find a critical value on table A4. Table A4 is the chi-square distribution. So we'll pull up table A4. All right, we need to be under column 0.05, that's right here. And we're going down to line 18 for the 18 degrees of freedom. And it looks like the critical value we want is right here, 28.869. Example 2. Find the alpha equals 0.10 critical value for the chi-square distribution with 4 degrees of freedom. Once again, we'll pull up table A4. We're going to look under column 0.10 and on line 4 for the 4 degrees of freedom. Column 0.10 down to line 4, that's going to bring us our critical value right here, 7.779. Example 3. Find the area to the right of 29.141 under the chi-square distribution with 14 degrees of freedom. So now we're kind of doing the opposite of that. We still want to bring up our chi-square table. We're going to be on line 14, but this time we know what the critical value is. So we're trying to find out what the area is that goes with a critical value 29.141. So when I pull up the chi-square table, I'm going down here to line 14, and I'm looking for 29.141. Let's see, that's 7.7, 21, 23, 26. Here it is, 29.141, and the area should be right here at the top of this column, 0.01. Example 4, find the area to the right of 46.979 under the chi-square distribution with 30 degrees of freedom. All right, so again, we're kind of doing the opposite. We're looking for the area when we already have the critical value and we have our degrees of freedom. So I'm going to pull up table A4. I'm going to be looking on line 30. We need to scroll down a little bit here. For 46.979, and here it is. And then if I read up this column, it should tell me the area, and it looks like it's 0.025. Example 5. A researcher wants to determine whether children are more likely to be born on certain days of the week. She will sample 350 births and record the day of the week for each. The null hypothesis is that a birth is equally likely to occur on any day of the week. Compute the expected frequencies. Okay, so what I'm going to do is I'm going to make a table to kind of organize our thoughts here. All right, so we're going to have our days. And we've got Sunday, Monday, Tuesday, Wednesday. I've already used T for Tuesday, so I'm going to put an R in here for Thursday, Friday, and then for Saturday we can just put an S with a little tiny a beside it there. Okay. All right, now the next one, we want the probability. Well, it says that the probability that a child is born is equally likely to occur any day of the week. And since there are 7 days in the week, the probability that a baby is born on Sunday is 1 out of 7. But since it's equally likely on any day, that means that all of my probabilities are going to be 1 out of 7. Now this is convenient, like I said, for organizing your data, but if your probabilities are all the same, it's not really necessary. This is actually better when you have different probabilities up here. All right, on my last line down here, I'm going to put the expected frequency. Now remember, to find the expected frequency, we're going to multiply n times the probability for each one of my days of the week. And n, they told me, right here is 350. So 350 times 1 over 7 for Sunday, that's going to give me 50. And then since we have the same probability for Monday, that expected frequency is going to be 50. And then for Tuesday, Wednesday, Thursday, Friday, and Saturday. Example 6. A researcher wants to test the hypothesis that births are more likely to occur on the weekdays. The null hypothesis is that 17% of births occur on each of the days Monday through Friday, 10% occur on Saturday, and 5% on Sunday. If 350 births are sampled, find the expected frequencies. All right, so I'm going to make my table again. We've got our days, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. All right, and then for my next line, we're going to have the probability. So on Sunday, the probability that a baby will be born is 5%, which as a decimal is 0.05. The probability that a baby is born on Monday is 17%. So this is 0.17, and in fact, it's 17% on all the days, Monday through Friday. And then we get to Saturday, and the probability changes to 10%. So this is a decimal is 0.10. All right, and on our last row here, we're going to compute the expected frequencies. And remember, all we want to do is multiply the probability, each of the different probabilities, times n. All right, so for Sunday, that's going to be 0.05 times 350. And that's going to give me 17.5. All right, from Monday through Friday, we're going to have a probability of 7.17 times 350. And that's going to give me 59.5. Oops, 59.5. And then for Saturday, we're going to have 0.10 times 350. And that will give me 35. Okay, let's see if we can fix this one. Because I messed this number up right here. There, that looks better. Example 7. Following are observed frequencies for 5 categories. Part A, compute the expected frequencies for testing the null hypothesis. P1 is 0.3, P2 is 0.25, P3 is 0.2, P4 is 0.15, and P5 is 0.1. All right, remember our expected frequencies, and I'm just going to put a new column, our new row right here underneath everything. This is going to be n times the probability. I'm going to put these probabilities up here at the top. So we got 0.3, 0.25, 0.20, 0.15, and 0.10. We need to know n. Now I can figure out what n is by adding up all of my observations down here on the bottom row. So 25 plus 14 plus 23 plus 6 plus 2. All right, let's put that in the calculator and see what we get. And this is giving me 70. All right, so for category number 1, I want to multiply the probability 0.3 times n of 70. And this is going to give me 21 as an expected frequency. For category 2, I'm going to multiply its probability 0.25 times n, which is 70. This is going to give me 17.5. For category 3, we're going to multiply its probability 0.2 times 70, and that's going to give me 14. Then for category 4, we're going to multiply 0.15 times 70, and that's going to give us 10.5. And then finally for category 5, we're going to multiply its probability 0.10 times 70, and that's going to give me an expected frequency of 7. All right, so the bottom row down here, this is our expected frequencies. This is part A. Part B, one of the observed frequencies is less than 5. They're talking about this one right here. Is the chi-square test appropriate? Well, remember, the test, to see if the chi-square test is appropriate, we need to be looking at our expected frequencies. And as long as everything in the expected frequency row is greater than or equal to 5, we're okay. And if we take a look down here, all these numbers are in fact greater than or equal to 5. So yeah, the chi-square test is going to be appropriate. And so here it is. Yes, it is appropriate because all the expected frequencies are greater than or equal to 5. Okay, part C. Now we want to compute the value of chi-squared. All right, let's remember the formula for our chi-square. This is equal to the sum of all of our observed values minus our expected frequencies divided by the expected frequency, and then this one is going to be squared. So this is going to be a long problem. Our chi-squared is going to be our observed value 25 minus the expected frequency 21, and we're going to square that and divide it by 21, plus our next observed value 14 minus its expected frequency 17.5 squared divided by 17.5, plus our third observed value 23 minus its expected frequency 14 squared divided by the expected frequency 14, plus our fourth observed value 6 minus its expected frequency 10.5 squared divided by 10.5, plus our last observed value 2 minus its expected frequency 7 squared divided by 7. And then we need to put all this in the calculator and see what kind of a value we're going to get back for chi-squared. And we'll round it to 3 decimal places. And this is giving me 12.748. All right. Now for part D. How many degrees of freedom are there? The degrees of freedom is the number of categories minus 1. So in this case, our number of categories is 5. So 5 minus 1, or 4. All right. Now we want to find the critical value at alpha equals 0.05. So we're going to pull up table A4. We're going to be looking on line 4 and under the column 0.05, and we're going to figure out what that critical value is. All right, so line 4, 0.05. That's right here. It looks like our number is 9.488. 9.488. And we want to know if we're going to reject the null hypothesis at the 0.05 level. Well, let's take a look at what's going on. We got our chi-squared distribution. We have our critical value right here at 9.488. And this area back here is 0.05. And the critical value we found on the previous page was 12.748. So on my picture, that's going to be back here. This does fall inside the shaded region, so yes, we are going to reject the null hypothesis. All right, letter G here, find the level alpha equals 0.01 critical value. So we're still going to be on line 4 for the degrees of freedom. Now we're going to look under the column 0.01. Let's pull up table A4. Here we go, 0.01, 1, 2, 3, 4. This is going to give me 13.277. So our critical value, 13.277. And for part H, we want to know if we reject the null hypothesis at the 0.01 level. Well, again, let's take a look at the picture. We've got our chi-square here. And we know from this point on, the area in this part of the curve is 0.01. And this point right here is 13.277. And the critical value we had, 12.748, that's going to be back here behind this because it's less than. And so actually for H, we are not going to reject the null hypothesis because our test statistic here, the chi-square, is not more than the critical value. It doesn't fall in the shaded area back here. Example 8. We have a table here that's got our 5 categories and our observed values. For part A, we want to compute the expected frequencies for testing the null hypothesis. The probability of category 1 is 0.4. The probability for category 2 is 0.3. The probability for category 3 is 0.1. The probability for category 4 is 0.15. And the probability for category 5 is 0.05. Okay, so once again, I'm just going to write the probabilities right here above in the table. So 0.04, 0.03, 0.01, 0.15, and 0.05. And I am going to add another row in down here for our expected frequencies. And I need to know what n is equal to. And remember, I can find that just by adding together all of my observed values right here. So 25 plus 14 plus 23 plus 6 plus 2. I think we did that in a previous slide. Yes, we have the same numbers here. So once again, we're going to have n is equal to 70. All right, for category 1, I'm going to multiply its probability 0.4 times 70. And this is going to give me 28. For category 2, I'm going to multiply its probability times 70. That's going to give me 21. For category 3, I'm going to multiply its probability times 70. That's going to give me 7. For category 4, I'm going to multiply its probability times 70. And that's going to give me, I think it's 10.5. Yeah, 10.5. And then for category 5, I'm going to multiply its probability, 0.05, times 70. And that is going to give me 3.5. All right, so all of our expected frequencies are down here along on the bottom row. Okay, part B. Is it appropriate to perform a chi-square test for the hypothesis on part A? Well, no, it's not. Because remember, if we look at our expected frequencies, this guy right here is ruining everything. All of our expected frequencies need to be more than 5. This one's less than 5, so a chi-square test is not appropriate. And down here is our explanation. It is not appropriate because all of the expected frequencies are not greater than or equal to 5. This one right here was actually less than 5.